Hello everyone, today we are going to understand a very simple and a fundamental concept of physics, that is the block on an inclined plane. So suppose this is my inclined plane, inclined at an angle of theta. There is a block of mass m, a downward force mg mg acts on the block. Then we can resolve this force into two separate components. One is the cos component, and from geometrical methods we know that this theta and this theta are equal. This one is our mg cos of theta. We know from the concept of vectors we have vectorially represented this part, and this one is mg sin theta. This is the sine component, mg sin theta. So now we have two parts, that is the mg sin theta and the mg cos theta. Another very important force that is acting is the upward, or the reactionary force that is acting upward. Wait a minute. This one is acting, it's called R, and this one is acting just up in the opposite direction of mg cos theta. So we can say that R balances mg cos theta, right? So if R balances mg cos theta, then R minus mg cos theta would be equal to 0, or R is equal to mg cos theta. R is equal to mg cos theta. This is one of the equations that we got, right? From this diagram we can say that R is equal to mg cos theta, and mg sin theta, right now we are not applying any force. Okay, so if I'm gonna apply a force in this direction, suppose this force is F. Okay, suppose this force is F, then I can say that F plus mg sin theta causes the motion, right? F plus mg sin theta is responsible for the motion of the body, that is equal to ma, if I'm applying a force in the downward direction. Okay, if I'm applying the force in the downward direction, then I'm getting this equation, that F plus mg sin theta is equal to ma. Then our acceleration is equal to F plus mg sin theta, by m. That's obvious, right? So this is our first equation for acceleration. The first equation for finding out acceleration. Okay, so in this case, A is equal to F plus mg sine theta by m. If a force is applied in the downward direction, then it equals with mg sine theta, then it adds up with mg sine theta to produce motion in the body. And you need R, this is the reactionary force, to balance this mg cos theta. Okay, this is the first case. Second case, in the second case, suppose a body, again this is our inclined plane, this is the angle theta. I think the inclination got a little bit more, but other than that everything is fine. This one is mg, and this one is mg cos theta. The angle between mg and mg cos theta is theta. Vectorially we know that the theta part is the cos theta, right? The base component, and this is a perpendicular component. There's a slight mistake. This should be exactly parallel to your slope, or the inclined plane. So this is mg sine theta. Okay, and again in this case R balances mg cos theta. So it's exactly the same diagram, only this F force is not present here. So in this case, suppose I'm trying to prevent the body from falling down, then I'm applying an upward force F. Note, here I am not considering friction. For a friction, for a video, for a body that is having friction, I mean, in real life we have friction, of course, but in this case I'm not considering friction. I will make a separate video for it. Considering friction, then we'll have F plus F in this case. Okay, but for now we are applying a force upward that is against this mg cos theta. Note that this force doesn't exactly balance mg cos theta. If it balances mg cos theta, then the body is in equilibrium, because R balances mg cos theta and F balances mg sin theta. Sorry, mg sin theta. I'm telling mg cos theta all the time. Then F balances mg sin theta, R balances mg cos theta. Then in this case, the body remains in equilibrium. So neither it's falling nor it's going up. But in this case, I'm considering, in the second case, I'm considering that F is greater than mg sin theta. Here, F is greater than mg sin theta. So if F is greater than mg sin theta, if F is greater than mg sin theta, then I can say that um, this F, here we were, the direction of F and mg sin theta was the same, so F plus mg sin theta got added. Now this thing holds for each and every case we'll be talking about now, because R is always balancing mg cos theta. Okay, R is always balancing mg cos theta. In each and every case, R is always balancing mg cos theta. Only this equation is gonna change, or this acceleration is gonna change. In this case, the acceleration here, F minus mg sin theta, that is F is in a different direction from mg sin theta, causes a motion upward. I have written F in front, and then I have given ma. That means the motion is being caused upward. See this case, F, and F is greater than mg sin theta. So in this case, F is greater, and so F is creating this motion ma. Great. Then if this is our equation, then acceleration is equal to F minus mg, minus mg sin theta, by m. And this is our second equation. This is our second equation. So what was the first equation? The first equation was acceleration is equal to F plus mg sin theta, because f and mg sin theta are acting in the same direction to push the body down the slope at an inclination theta. The slope is at an inclination theta. Okay. Then in that case we are getting acceleration is equal to f plus mg sin theta by m. In this case we are getting acceleration as f minus mg sin theta by m, because I'm trying to pull the body upwards in this case. Okay. Here f acts in an opposite direction to mg sin theta. Now there is a third case. There is a third case, and this third case is same thing, same diagram. Same diagram with mg downwards and theta mg cos of theta and mg sine of theta, and this r balances everything. I mean balances the mg cos theta in upward direction. So in this case I am not applying any force. Then again naturally r is equal to mg cos of theta. Okay, this is lagging a bit. Mg cos theta, right? R is equal to mg cos theta. I told you that in each case this equation remains the same, because reaction force always balances mg cos theta. That's the eternal truth in our inclined plane problems. Okay. And when we study friction, we'll come to know that R is actually F equal to mu R, and R we have to substitute with mg cos theta. Then we'll get the angle of repose and all. But that was later on. First, we'll consider a frictionless surface. We are talking about discussing a frictionless surface now. Now R is equal to mg cos theta. In this case, since there is no force, no external force applied, like the experimenter is not applying an external force, the only force that acts on the body is mg sin theta. Apart from mg cos theta, mg and r, the only force that tends to bring the body down the slope is mg cos sin theta. Then here in this case mg sin theta is the only cause for ma. So m and m get cancelled. We are left with a equals to g sin theta. A equals to g sin theta. This is our third equation. So what are the equations we got? We got if no force is applied, that is F external force F is equal to 0, then the acceleration is only due to the mg sin theta, or acceleration is g sin theta equal to g sin theta. If a force is applied in the downward direction, acceleration is equal to F plus mg sin theta. Both the forces are added by the mass of the body m. And the last equation is where F is greater than mg sin theta and F pulls the body upwards. Then F minus mg sin theta equal to ma. Then A equal to F minus mg sin theta by m. This is for pulling the body upwards, the inclined slope. Hope you guys enjoyed it, understood it. It's a pretty easy topic in Newton's law of the motion, and I feel it very intuitive for students who are learning the Newton's law of the motion for the first time. It's really intuitive. Okay. So if you liked it, please don't forget to like, comment, and subscribe to the channel. You'll get daily physics updates like this. Okay. And in the next video, I'll come up with friction surfaces. Surfaces having friction. We'll consider friction. Same thing, but we'll consider friction. Bye until then.